So we decided that number 13E was where the f prime is positive because the function is increasing, and f prime is increasing because it's concave up. So the second derivative would be positive. Okay, questions on the homework? Anybody or? Yes, Sally. Number 9. Yes. So on number 9, we want the point on the curve y equals x squared minus 1, which is going to look like this. Oh, that minus 1, sorry, that was plus 1. How about like this? So here's f of x equals x squared minus 1. And we want the point that's closest to 0, 2. So this is like the hardest justification of why something is an absolute max or an absolute min. Because I don't think we can restrict our domain in any way. So we're taking any point on this curve of all those choices, which one or ones are going to be the closest to 0, 2. Does that kind of make sense what we're asking anyway? So as you pick different points along here, you can see what its distance is to that point. Somewhere there's a closest one. And we would expect, because of the symmetry of this, that if we have one that's closest here, there's going to be another one on the other side that's also that same distance away. So we would kind of think there might be two that are the same shortest distance. The problem is, I don't see any reason where we can restrict the domain. So our domain here is going to be negative infinity to infinity. And that makes it tough. And we're going to find that we have multiple critical points. If we have only one critical point, we can make the justification by doing it on the line and saying, you know, the derivative goes from negative to positive, therefore it's a relative min. And if it's the only critical point on the domain, then that would make it the absolute min. And that's not going to work in this case. So this is the hardest one. But it's good to see. So our distance formula, the distance between 2 points is x2 minus x1 squared plus y2 minus y1 squared. Okay, that comes from the Pythagorean theorem. So our point, we're going to say one of our points is 0, 2. The other one is any point that's on that curve. And so the x can be whatever you want as we let x go from negative infinity to infinity. Because it's on that parabola, its y coordinate must be x squared minus 1. So this is our x2, y2, and this is our x1, y1. So our distance is going to look like the square root of x minus 0 squared plus the x squared minus 1 minus 2 squared. Okay, so far? So that's just x squared. And this is going to be x squared minus 3 squared, which is going to be the first one squared, twice the product plus the second one squared. Is that okay? And we can combine the x squared terms. So our distance is x to the 4th minus 5x squared plus 9. This is what we're trying to minimize. We're trying to find the absolute minimum of this function on this domain. But this is a really, really messy function because of that square root. It's a chain rule. It's going to get really, really hard to work with. So we can, if we notice, say that the value of x that makes this square root the smallest is the same value of x that makes this without the square root the smallest. That is, as you look at numbers, you know, if you imagine you look at numbers and you order them, if you take the square root of those, that doesn't change their order. Like square rooting these doesn't somehow make a bigger number smaller. Does that make sense? So the value of x that makes this the smallest is the same value of x that will make this without the radical. And it's way easier to work with it without the radical. But you have to say that. So I'm going to say the same value of x that minimizes d minimizes, I'm going to call it d hat, without the radical. Okay? So now it frees me from having to take a derivative with that huge chain rule. So now I'm going to look to the minimum of this. And whatever value of x that I find that minimizes this also minimizes this. That's what we're looking for. So I'm going to take d hat prime, and that's going to be 4x to the third minus 10x. So we're going to set that equal to 0 because we're looking for critical points. And we're going to, I guess, factor out that 2x, leaving a 2x squared minus 5. Is that okay there? And so we're going to take the 2x squared minus 5 equals 0. So 2x squared is 5, x squared is 5 halves. X will be positive or negative square root of 5 halves. Yuck. And we also get a 0 from there. These are our critical points. There's 3 of them. That's the bad news. So we can't do a number line thing. That's not going to help our cause. Because no matter what happens for the signs here, because we don't have a closed interval domain, no matter, if this was, I don't even know, negative, positive, or something, we don't know what's going on down there or what's going on up there. So there's no point in even doing this. It's not going to be a logical argument for why one of those is the smallest. So we can't do our candidate test because it's not a closed interval domain. So we do a kind of a modified candidate test. We're going to plug these values into our d hat function to see which is the smallest. And since we can't plug these in, we're going to take the limit as x approaches those ends of our domain. And that will suffice as the candidate test. Now we're really hoping that the limit as we approach these does not turn out to be the smallest value. Because if that happens, we're going to say there isn't the smallest value because it's not going to equal that. And then it's kind of a silly problem to ask you to find something that we can't find. So we hope that doesn't turn out. So I'm going to take, here's our candidate test. We'll take the limit as x goes to infinity of d hat. So here is our, I'm going to just emphasize our d hat. So here's our d hat. Now, as x gets really, really big, the behavior is going to be determined by the highest power of x. So as we put in 1,000, a million, a billion to the fourth power, that's growing large without bound. We're going to say that's infinity. Well, that's good, because I don't think that's going to be our smallest value. Okay, now we take the limit as x goes to negative infinity of d hat. Same story. The highest power of x is going to dominate, but because it's an even power, when you take a very, very large negative number to the fourth power, it still goes to positive infinity. You can heave a sigh of relief. Good. Now we have a chance of getting an answer. So now we're going to take d hat at 0. So if we plug in 0 into d hat, we're going to get 9. Now we're going to evaluate d hat at the square root of 5 halves. See, we're looking for the smallest value here. So when we plug square root of 5 halves into the fourth power, squaring it makes it 5 halves. Squaring it again makes it 25 fourths. Squaring it is back to 5 halves. 5 halves times 5 is 25 halves. So that's a minus 25 halves. And then we have a plus 9. Is that okay? So this is going to be 50 fourths. So we have a 25 fourths minus 50 fourths. is going to be a negative 25 fourths plus 9. So we can see that this we're going to get smaller than this, right? So we can say 9 is 36 fourths. 36 fourths minus 25 fourths is, we don't got that kind of time. 11 fourths. Okay? Now we're going to evaluate this at negative square root of 5 halves. Well, since these are both even powers, plugging a negative, plugging the positive, they're going to be the same. So we're going to be exactly the same thing. Is that okay? So these are the smallest in our list. So this is the shortest distance. Well, actually, this is d hat, the smallest d hat would be. The real distance would be the square root of 11 fourths. But that's okay, we don't need to know that. We just know the smallest distance, the shortest distance between any point on this curve and 0, 2 is going to be when x is equal to a positive or negative square root of 5 halves. And our justification is our work. You don't have to write a sentence or anything else. Our work in the case of a candidate test or a modified candidate test stands just on there, as long as you showed your work. Now, the question was, what are the points that are closest? So we have the x values. We need their y coordinates. So these points on here have their x coordinate, and then their y coordinate is going to be x squared minus 1. So our 2 points are going to be the positive and negative square root of 5 halves. Squaring that makes that 5 halves minus 1, which is 2 halves, is going to be 3 halves. So there's 1 on either side, which kind of makes sense, I think, because of the symmetry of that parabola. Good to go? Let's just stop and see what we did. So part of what makes optimization so difficult is that you have to do this, how do you know it's the absolute max or absolute min? And there's kind of 3 scenarios that can happen. When you have a closed interval domain, you kind of go, oh, thank goodness. Because now you can use the candidate test. You're going to take the derivative, set it equal to 0, find the critical points. Where's the derivative of 0 undefined? See which ones are on your domain. Any that aren't, we just throw them out of interest anyway. Whatever survives that test, we plug into the original function and the endpoints. That's what we mean by the candidate test. The critical points and endpoints are candidates for the absolute max and absolute min. We are looking for the largest value of the function. We're looking for the largest y value. You plug those into the function. The biggest one is the maximum. The smallest one is the minimum. If it occurs more than one time, that doesn't matter. Whatever that y value is the maximum or the minimum. That's the best possible scenario. And that's the one on an AP exam you are probably 99% of the time going to see. But if you do have an open interval domain, now there's 2 subcategories of that. The best scenario there, of the less than best scenario, is that you have only one critical point. So if you can restrict your domain enough that there's only one critical point on that domain, then you can do it like you would be looking for a relative min or relative max. And if it goes, say, I'm just making this up, from positive to negative, you could say that this only critical point is going to be increasing, and then it's going to decrease over the entire domain. That means it's got to be the absolute maximum, right? So you would say it's a relative maximum because the derivative changed from positive to negative. It's an absolute maximum because it is the only critical point on the domain. The worst scenario, the one you don't want to see, is one where you have an open interval domain and you have more than one critical point. It is not a logical argument that if you have more than one critical point, say you had two. Suppose you had two critical points and an open interval domain. It is not a reasonable argument to say this is a relative maximum. It's the only relative maximum on the domain, therefore it must be the absolute maximum. That is a faulty logical argument. Can you see that if this is what we're looking at, this thing could be increasing, decreasing, as your relative max, but then it's going to increase, we don't know how far. And you can't plug in an endpoint because there is no endpoint. So that is not a reasonable argument. So that's why if you have more than one critical point, then you're back where we are here, looking at the limits as you approach the endpoints. It's a hard argument to make and a lot to take in when this is all new. Does that help? Questions? We got 3 minutes. Okay. Can we just find and let's do a second derivative test. Use the second derivative test to find a relative extreme. So f of x is equal to x to the fourth minus 2x squared. You have 2 minutes. Hurry up. Remember, on your homework tonight, you just do the odds on that. We're going to stretch our review out here a little bit. We're testing Friday on chapter 4. A week from Friday, we do the semester test. Oh boy. Some people would rather move than have to do that. Just saying, it's been done. Oh, that's a bummer. Oh, are they all 0? Oh, yeah. Did I do that right?
That's not the second derivative.
Oh, that's the first. No wonder they're all 0. 19. What? Okay. Okay. I was hoping to get 1 to be 0, but I guess I goofed that up. Oh well. So here, because this is less than 0, we're going to get a relative max. And you'd have to go 0 back in the original, makes it 0. And these are going to both be relative min. If it had been 0, what would we have had to, what would we do? And we say we don't know. So if you have to know if the relative min max, you have to go back and use the first derivative.
See you later.
All right, I'm looking forward